In this lecture, we are going to provide an introduction to the subject of dynamics and then provide the mathematical background that is required in order to be able to formulate problems in dynamics. So, dynamics is really a subset of mechanics. So, let's write down Introductory Concepts. So what we're really going to be dealing with in this course is mechanics. We're going to be dealing with dynamics, but mechanics is the study of the response of systems, of physical systems, to actions that are applied to the system. Now within that, which is the focus of this course, is going to be dynamics. So what is dynamics? At least from a mechanics standpoint, what is dynamics? So dynamics is the motion of physical systems in response to actions applied to the system. Now, dynamics itself is actually broken up into two pieces, and we're going to talk about both these pieces in this class, but right now I'm just going to give you a high-level view of it. The two pieces of dynamics that are critical to being able to characterize motion of physical systems are kinematics and kinetics. These are the two halves, if you want to call it that. So what is kinematics? Kinematics is the study of motion, or of the geometry, I should say, the geometry of motion without regard to the cause of the motion. Now, what we're looking for in kinematics is we're trying to characterize things like position, velocity, and acceleration. And then for rotation, we're also looking at angular velocity and possibly angular acceleration. Now, the important thing in kinematics is studied, like I said, without regard to the cause of the motion. So we're not interested in kinematics and what causes the motion. We're interested in trying to understand the geometry of the motion itself. Kinetics is where we actually get into the cause of the motion. So kinetics is the study of motion that arises from a cause, and that cause is also what's called an action. And actions applied to physical systems take on two fundamental types. They are forces and torques. Well, they're torques, but they're moments really, but we'll call them torques. And what we're going to do in this course is we're going to link these two things. So what we're going to do is we're going to take kinematics, we're going to be studying kinematics, we're going to be studying kinetics, and these two pieces are linked by what are called the laws of mechanics. The laws of mechanics in this course comprise two different sets of laws. For particles, we have Newton's laws, and for rigid bodies, we have Euler's laws. So what this provides, in a sense, is that we get the following framework, is that this course is about the formulation of a Newton-Euler framework for dynamics. And we will get into the details of all this as we move forward. But in order to be able to do this Newton-Euler framework, we need a mathematical background. So that's the first thing that we're going to be talking about in this class, is a mathematical background. So the mathematical background for all of this is what's called vector algebra. And so we're going to be discussing vector algebra as the first topic in the course. So vector algebra is basically the study of algebra of geometric vectors. This is all geometry. It's called vector algebra, but it's really algebra of geometric quantities. So we start with the most basic constructs in dynamics, which there are two. There are what are scalars and vectors. Now, the first thing we need to define is we need to define a scalar and a vector. So what's a scalar? A scalar is any quantity that can be represented as a real number. And we're not going to be dealing with anything other than real numbers in this course. So, for example, if I say B is a scalar, suppose I specify. I'll say, suppose that B is a scalar. Then that implies that B is an element of the real numbers, where this notation here is the set of real numbers. That's a set of real numbers. Now, given the fact that we have scalars, we have to define vectors, because scalars only have magnitude. So scalars only have magnitude. Well, magnitude in the sense that they don't have any direction. Maybe that's a better way to put it. Let me write that down. Scalars have no direction associated with them. Scalars are directionless. So, in order to be able to do mechanics, though, we need to deal with direction. So, in order to deal with direction, we have to deal with what are called points and vectors. So, the first thing I'm going to define is I'm going to define a point. A point is a zero-dimensional object in what is called three-dimensional Euclidean space. Now, Euclidean space is denoted E3. That's Euclidean space. And when we talk about points, what we mean is points lie in three-dimensional Euclidean space, and Euclidean space itself is the physical space in which we live. But what it really is we say Euclidean space is a model for the geometric space in which objects live. So what we're really saying is that, let's suppose that I abstractly draw like a blob, and I call that blob three-dimensional Euclidean space. Then points lie in three-dimensional Euclidean space. So I can just label these points. Suppose I label one of them and just call it P. So if P is a point, then P is an element of E3. Okay. Now, once we have points, we can actually define vectors, and we can define vectors from translations of points. So the way we can do that is as follows, is that let's suppose I take another point, I call that point Q. Let's let's denote Q by this point right here, Q. What I can do now is I can take the line connecting P and Q, and I can draw that line, and that direction from P to Q and the distance from P to Q defines what's called a vector. So let's suppose that I'm going to say that dP, or D, we'll do it this way, dQP is the distance from Q to P. And then what I'm going to do is I'm going to say, well, given that distance, I'm going to say that the direction from Q to P, I'm going to call that direction, I'm going to call that UQP, which is the direction from Q to from Q to P. And what I'm going to do is I'm going to define that direction with an underbar. So if I call this vector that goes from Q to P, let's suppose I call it B, and I denote that with an underbar. So vectors are denoted as underbars. And now what's the definition of a vector? So a vector is any quantity that lies in E3 with both magnitude and direction. So suppose if B is a vector, suppose that B, the way I drew it before, is a vector. Now, the magnitude of the vector, B in this case, is dPQ. That's the magnitude of B. The direction, UPQ, this is the direction of B. So what we could do is, we'll simplify this a little bit in a second, but B can be written as D, sorry, I used QP, so let me flip these. QP, QP, dQP times UQP. But in order to make this a little simpler, rather than writing all that, we could say alternatively, we could write B is equal to some scalar B times U, where the scalar B is the magnitude of B, and this quantity U is the direction of B. So vector has a magnitude and a direction. Now, once we have the definition of a vector, we can actually define operations on vectors. So the two most fundamental operations on vectors, the two most fundamental operations on vectors are what are called the scalar product, which is also called the dot product, and the vector product. So the scalar product and the vector product. Vector product is also known as the cross product. So I'm going to define both of these. First one is the scalar product. And the scalar product is the scalar product between two vectors. So we define the scalar product with an operation called dot. So let A and B be vectors. Then the scalar product between A and B is defined as A dotted with B, which is equal to, and now I'm going to introduce some new notation, the magnitude of A times the magnitude of B times the cosine of the angle between them. So let's start denoting things and we'll see what's going on here. Here's A, here's B, here's the angle between A and B, which I'm going to call theta. So theta is the angle between A and B. Now, this notation with the double bars is actually not random notation. It's actually systematic notation. This notation is the magnitude of whatever the argument is that's inside the bars. So when I say the magnitude of A, I can alternatively denote it with the double bar the way I have it. Now once you have that, if you look back here, you'll see something. So I have this notion of this scalar product, and since A is a magnitude, it's a real number. Sorry, the magnitude of A is a real number, the magnitude of B is a real number, and an angle is a real number, so the cosine of that angle is also a real number. So this result is a scalar. So A dotted with B is a scalar, which is why this is called the scalar product, which means that A dotted with B is an element of the reals, because scalars are elements of the reals. So now once I have that, I can actually now define the magnitude of A from this result, which is that the magnitude of any vector, I'm always using B before, so we'll use B. Any vector B is then defined as follows. We can say that B dotted with B is equal to the magnitude of B times the magnitude of B times the cosine of the angle between B and B. But what's the cosine of the angle between B and B? It's 0, right? So it's cosine of 0, right? If I take the dot product of B with B, I get two vectors that are in the same direction. So if I'm taking the dot product between a vector with itself, then the angle between the two vectors has to be 0 because it's the same vector in both cases. So from this tells me that the magnitude of B squared is equal to B dotted with B, right? Because the cosine of 0 is equal to 1. Notice that the cosine of 0 is equal to 1. So I get B dotted with B is equal to B squared, which tells me that the magnitude of any vector B is equal to the square root of B dotted with B, which is also equal to B dotted with B raised to the 1/2. So now I have the definition of the magnitude of a vector. The next thing we need to do is we need to define this concept of orthogonality. So orthogonality. Orthogonality is actually fairly straightforward to define once we have defined the scalar product. But orthogonality is defined as follows. If I say A and B are vectors again, so let A and B be vectors. Be vectors. The vectors A and B are orthogonal if A dotted with B is equal to 0 and neither A nor B is the 0 vector. So A is not the 0 vector and B is not the 0 vector. In other words, they both have to have non-zero magnitude. If either of these vectors has 0 magnitude, this doesn't make any sense, and that shouldn't have an underbar. It should just be a 0. So two non-zero vectors, if I take the dot product between them and that dot product is 0, I wind up getting that these two vectors are orthogonal to one another. That's the definition of orthogonality. So once we have that, we can actually use orthogonality in the next in the next definition that we're going to come up with. The next definition is what's called the vector product. So now I have a definition of orthogonality. Once I have that definition of orthogonality, I can use it to construct what's called the vector product. So the vector product works like this. Let A and B be vectors. Then the vector product between A and B is defined as follows. We say A, and then we use the symbol cross. A cross B is equal to the magnitude of A times the magnitude of B, but now we know what the magnitude of a vector is, times the sine of the angle between the two vectors, times a vector which I'm going to call n. And I'm going to define n in just a minute. But before I do that, let's suppose I call C A cross B. So let's go back and draw these vectors. There's A, and there's B. And again, there's the angle between A and B. This direction, or this vector that results from this, is actually the cross product of A with B. It's A cross B, which is going to be equal to C. The vector n lies along this vector A cross B. And it's such that it's orthogonal to both A and to B. So n is orthogonal to both A and B. And it's orthogonal in what's called a right-handed sense. And I'll define that in just a second here. So what's important about the orthogonality, for starters, is as follows. Is that if n is orthogonal to both A and B, then we know that A dotted with n has to equal 0 and B dotted with n has to equal 0. Okay? So that means that since A cross B lies in the direction of n, that implies that A cross B dotted with A is equal to 0, and A cross B dotted with B is equal to 0. Now, one thing that I should have said here is n is a unit vector. This is a unit vector. So that means that the magnitude of n is equal to 1. Now I have to define this thing called a right-handed sense. So what's called the right-handed sense. So the right-handed sense means we start with A and curl our fingers, or curl the fingers of the right hand. Write this a little bit better. Curl the fingers of the right hand in the direction of B. So basically what that means is we're going to sweep like this. A and then B, we're going to sweep that way. So our fingers are curl, the curl of the fingers goes this way. And the thumb is going to point whatever direction the thumb is pointed of the right hand. So this is the thumb of the right hand. This is what's called a right-handed sense. So this whole thing here comprises what's called a right-handed sense. And that actually creates what's called the right-hand rule, which I'll get into in just a minute. But n lies in the direction. So n is orthogonal. I said it already once, but I'll say it again. N is orthogonal to A and B in a right-handed sense. Now what we can do is we can use the cross product or the vector product together with the scalar product to define what's called a coordinate system. So that's the next thing we're going to do. So is that vectors need to be expressed in ways that make it possible to do or to perform algebraic calculations. So in order to be able to do that, we need to be able to provide measurement. In other words, we need a measurement device, if you want to call it that. That measurement device is what's called a coordinate system. So a coordinate system. So a coordinate system provides or is a device that enables measurement. This is not very legible. Enables measurement in three-dimensional Euclidean space. So the way we construct coordinate systems is as follows. So we're going to define a coordinate system now. So a coordinate system is comprised of one, an origin, and an origin which is a point from which distances are measured. And then two, a right-handed, now we know what a right-handed sense is, so we're going to define a right-handed orthonormal basis. So the way we denote these is as follows, is that I'm going to draw it schematically and then we can figure out what to do here, which is that I'm going to put down 3 unit vectors. I'm going to define these 3 unit vectors as E1, E2, and E3. So this construct here, E1, E2, E3, is a right-handed orthonormal basis. And then I'm going to have a point here, which I'm going to call O. And O is what I'm denoting as the origin. The origin of the coordinate system is at a point called O. Now, if I have a vector, let's suppose I call that vector B. Okay? First, what I have to do is I have to define what these basis vectors mean. So the basis vectors have the following properties, which is a right-handed orthonormal basis, which, for the purposes of this class, will just be denoted as a basis from this point forth, but I'll write it all out in the beginning. Right-handed orthonormal basis. And like I said, we'll abbreviate that from this point forth. I'll just call it a basis because we're always going to be dealing with right-handed orthonormal bases. Has the following properties: is that 1, E1, E2, and E3 are mutually orthogonal. What that means is, it means that if I take EI dotted with EJ, it's going to equal 0 if I is not equal to j. The second thing is that E1, E2, and E3 are unit vectors. This means that EI dotted with EI means any of these vectors dotted with itself is equal to 1, right? This is for I equals 1, 2, 3. This is also for I and j equals 1, 2, 3. So if I want to be a little bit more complete about this and say I, j equals 1, 2, 3, I not equal to j. Okay? So, and then the third thing is that these basis vectors, this triad, E1, E2, E3, forms a right-handed system. Now, what do I mean by right-handed? What I mean is, let's go back to this picture I have here. It means that because these vectors are orthogonal to one another, so let's take this from the cross product or the vector product standpoint. It means that if I take E1 crossed with E2, I get E3. This is what's called the right-hand rule. It means that if I, without having to go back to that other page, if I write E1 cross E2, the right-handed system is completed by E3, and E3 is equal to E1 cross E2. See, there's a possibility here, without getting into a lot of details, that I could have picked this direction as my third direction. I'm drawing it with a dotted line so that as to not confuse it. In fact, you know what? Let's not even draw it as a dotted line. Let's put it in a different color. Let's put it in red and draw it as a dotted line. I could have chosen this direction, right? So this could have been the direction of, this could have been the direction of E3. But I'm going to put that in quotes. Could have been, right? But if I had chosen this direction in red as the direction of E3, then given that I'm doing the order 1, 2, 3, in that order, I'm ordering the basis vectors, E1 crossed with E2 is not going to equal E3 in this case, right? In this case, E1 crossed with E2 is not going to equal E3, right? Because E1 crossed with E2 has to be in the right-handed sense, in the direction of the curling your fingers from E1 to E2, your thumb is going to point in the direction of E3. So this would not be a right-handed system. So that would mean that's not right-handed. So I'm not going to choose the non-right-handed version. It's not right-handed. So I'm going to choose the right-handed version of this. It's not right-handed. All right? So I'm going to rule this out. So let's just cross this out in blue. So we're not choosing that. We're choosing the one that I drew originally, which is the one that preserves the right-hand rule. So this preserves the right-hand rule. the right hand rule. Okay? So now, once I have that, I can actually do things with it. So what I can do is I can project with the scalar product onto these three directions. So let's look at this. Let's see what happens here, okay? We know that E1, E2, E3 is a right-handed orthonormal basis. So that means, let's look at this. EI dotted with EJ is equal to, there are two possibilities. We've listed them. Let's put them together now. Which is, it's going to equal 1 if I is equal to j. Right? It's going to equal 0 if I is not equal to j. That's what we already said. So, if this is the case, now look what happens if I take this vector b and I project it along each of these directions. So I'm going to come up with what are called components. So the components of the vector b in the basis E1, E2, E3 are given as follows. We say that b dotted with E1 is the first component. B dotted with E2 is the second component. And B dotted with E3 is the third component. Now, what's significant about these components? What's significant about them is as follows. Is that let's suppose I write the vector. I'm going to write it this way. B is equal to B1, E1, plus B2, E2, plus B3, E3. Now, because these vectors, E1, E2, and E3, these basis vectors are orthogonal to one another, look what winds up happening. Is that B dotted with E1 is equal to B1, E1, plus B2, E2, plus B3, E3, dotted with E1. But that's equal to B1, and then I've got E1 dotted with E1, plus B2, E2 dotted with E1, plus B3, E3 dotted with E1. But these last two terms over here, this one and this one, are both 0 because these vectors are orthogonal to one another. And this one here, which is the one that is the vector dotted with itself, this is equal to 1. So what this tells me is it tells me that B1 is equal to B dotted with E1. And then we can do the same thing for the other two. So we can say similarly, B2 is equal to B dotted with E2, and B3 is equal to B dotted with E3, right? So what that allows me to do is now using a right-handed orthonormal basis, I can express the vector in this basis using three components. So this is the expression of B in the right-handed orthonormal basis E1, E2, E3. Now what's really important about this is I'm going to add to this picture now. Suppose I have this basis, E1, E2, E3. Let's draw this again so we can see this hopefully clearly. Suppose I pick another basis. I'm going to pick something else. I don't know what this is, but I'm just going to draw it. And in fact, let's draw it with a different color. Let's draw it with blue. Okay, so suppose I pick a new basis. I'm going to call this basis U1, U2, and U3. Now, if you look at Make that look like a 3. Suppose I draw the vector again. It's the same vector. I've got this vector here, b. Remember that if I express b in the original basis, I've got b is equal to b1 e1 plus b2 e2 plus b3 e3, right? But if I was to write that vector in the other basis that I've drawn here, u1, u2, u3, I'm not going to get the same components, right? This is the vector expressed in the other basis is going to be b1 prime u1 plus b2 prime u2 plus b3 prime u3. Now look at this for a second. You'll see that the basis u1, u2, u3 is not equal to the basis e1, e2, e3. So that means that, take any one of these, it doesn't make a difference, but let's maybe be a little bit general here. B dotted with ui is not equal to b dotted with ei. It can't be because the dot product of this vector b with any of these original basis vectors is going to give me a different value than if I take the dot product with these new basis vectors u1, u2, u3, because those directions aren't the same as the directions of e1, e2, e3. So, but we remember that b dotted with ui is the component of b in the direction of ui. In other words, b dotted with ui is what I'm calling bi prime in the in this new basis. So that tells me that bi prime is not equal to bi. In other words, what we're saying here is that the components of b, let's write this, the components of b in the basis u1, u2, u3 are not equal to the components of b in the basis e1, e2, e3. Now, the components aren't the same, but the vector is the same. So what that's saying is that, let's go back to this picture here. Notice that if I look in this picture, the fact that I've used two different bases doesn't change the vector. The vector is the same vector. B is the same vector regardless of the basis in which I express it in. So what that tells me is B is coordinate free. It does not have anything to do with coordinate systems whatsoever. But the expression, the manner in which B is expressed does depend upon the coordinate system. So what we learn from this is the following. We learned that vectors are coordinate free, but the expression of vectors depend upon the coordinate system, and really in this case we're dealing with bases, so we can say basis in which the vector is expressed. So it provides two different parts. One is the geometry, and one is the algebra. So vectors, we're going to do this again, just to remind everybody, lie in three-dimensional Euclidean space. So if B is a vector, it lies in three-dimensional Euclidean space. But the expression of the vector, so the expression of the vector, the expression of a vector is defined by the basis that is used and leads to three components. And we call those three components arbitrarily, I just call them B1, B2, B3 for the basis E1, E2, E3. Do it this way. And B1, B2, B3 are three real numbers. So if I stack these up, suppose I stack them up. Suppose I say B1, B2, B3. These three quantities don't lie in three-dimensional Euclidean space. They lie in three-dimensional real space. So these are the components of B in the basis E1, E2, E3, which we could actually compactly write it this way. If I could say B, when expressed in the basis E1, E2, E3, is equal to B1, B2, B3. And that provides a separation between the geometric vector, which has nothing to do with coordinate systems, and the manner in which that vector is expressed. So that's the formulation or the foundation of vector algebra that's used in dynamics, and we're going to use this over and over again in the class. And just to finish this up, all algebraic operations are defined the way you would expect them to be defined. So I've done it already, but to be a little bit more formal about it, we can write down, suppose A and B are vectors. Then A plus B is equal to B plus A. That's the commutative property. And then A plus B plus C is equal to A plus B plus C. That's the associative property. If I take a constant K and I multiply by a vector B, then that, if I take the magnitude of that, that's the same thing as the absolute value of K times the magnitude of B. Now, because K could be negative, there's nothing that says that K has to be a positive number. And these are just the usual operations that you know of from algebra. This is commutativity. Commutativity. Write this a little neatly. Commutativity. And this is associativity. Associativity. And then this is just multiplication by a scalar. Multiplication by a scalar. By a scalar. And again, that scalar could be negative, so when you take the magnitude, you have to take the absolute value. So these are all operations that are the commonly used operations of vectors, and all vector algebra is performed in normal way arithmetic algebra is performed. There's no difference. And when you write down the vectors and you express them in different coordinate systems, you do the algebra component-wise the same way you would otherwise associate with regular algebra. So that's going to be the end of this lecture, and we'll pick it up next time.